For generations, the Tsugaru Strait was a deadly geographic chasm, a violent stretch of ocean that isolated.
In September 1954, under the looming threat of Typhoon Maru, the commercial passenger ferry Toya Maru embarked.
The typhoon unleashed its full fury. The Toya Maru was pushed onto the rocks and capsized, claiming over 1,400 lives. The tragedy shocked a recovering post-war Japan. The ocean had proven too hostile, and the nation realized it could no longer return. In the wake of the disaster, the Japanese government made a historic, monumental decision. They would bypass the deadly sea nations. The proposal was staggering in scale. A 53-kilometer railway tunnel, with 23 kilometers drilled directly under the tunnels. The Tsugaru engineers had to calculate the undersea trajectory with absolute, flawless precision. A single millimeter of alert. In 1955, the initial survey teams arrived on the shores of Cape Tappy. Facing freezing winds and the battle had officially begun. The surveyors were ready to plunge deep into the dark, uncharted geology of the undersea abyss. To map the rock strata beneath the seafloor, geologists deployed seismic reflection surveys, detonating hundreds of dynamite charges.
The seismic data sent back a terrifying warning. The seabed was a chaotic geologic nightmare, filled with volcanic ash.
At its deepest point, the water was 140 meters deep, under the immense pressure of millions of tons of seawater. The core samples proved that the volcanic rock was highly fractured and saturated with water. Drilling through this gouge zone ounces. To mitigate the extreme geological risks, engineers proposed a dual-tunnel strategy. A small pilot tunnel would be drilled. On the shores of Honshu and Hokkaido, precise Tsugaru base stations were established. Before digging a single inch under this, in 1964, the Yoshioka inclined shaft began its descent. The miners were leaving the daylight. Every foot they descended, the air became warmer and more humid. The water began to seep through the rock, a constant reminder of the ocean weighing down above. The stage was set for the ultimate mechanical clash. The battle moved from the shoreline directly into the heart of the undersea fault lines.
The Japanese engineers placed high hopes on automation, deploying massive, state-of-the-art tunnel boring machines to drill the undersea pilot tunnel with high speed.
But the geologic reality of the strait was unforgiving. The soft, water-saturated volcanic clay was too weak to support the weight of the massive machines. The moving clay geological faults squeezed the machines like a vice, locking the cutter heads and trapping the multi-million-dollar TBM. Engineers realized that machines could not conquer the Tsugaru Strait. They had to return to traditional, high-risk manual blasting and hand-shield mining. Every day, workers loaded tons of dynamite into thousands of drill holes. The mountain beneath the seafloor was systematically shattered. With a single throw of an electrical switch, millions of pounds of dynamite blasted the mountainside, unleashing a roaring shockwave that could be felt for miles. The key to the excavation was speed. Stevens' railway conveyor belt had to move the debris out of the cut as fast as the shovels could dig. But the mountain fought back. The unstable geology of Panama triggered catastrophic landslides, entire humans. By 1973, despite the failures of the massive boring machines, the pilot tunnel dug from Sunset. The deeper they dug, the more dangerous the geologic conditions became. In May 1976, the pilot tunnel reached. At first, it was a whisper, a tiny stream of highly pressurized seawater hissing through the rock fissures under over 2 megapascals of crushing pressure.
Then, the mountain fractured. Seawater exploded into the tunnel.
The flooding was catastrophic. The miners fled for their lives, fighting the rising torrent that threatened to seal the tunnel and drown 40,000 workers. The only line of defense was the massive steel bulkhead gates. Despite weighing several tons, these gates had to be closed manually against the extreme force of the water. The entire dewatering system was pushed to its absolute limit. High-capacity centrifugal dewatering pumps were activated, fighting to empty the flooded chambers.
To guide the massive ships safely through the narrow concrete chambers, they designed electric locomotive mules. Running on
Gatun Dam successfully blocked the wild Chagres River, creating Gatun Lake, the largest artificial lake of its time. The entire canal was powered by electricity, generated by the water flowing out of Gatun Lake through a specialized hydroelectric.
By late 1976, After months of desperate battle, the pumps finally won the war. To seal the tunnel against the extreme hydrostatic pressure, the Japanese engineers developed a revolutionary chemical grouting engines. They poured millions of cubic yards of concrete to build the lock walls. It was an unprecedented material operation, Hidden deep inside the massive lock walls was a complex network of hydraulic culverts. The lock gates were masterpieces of structural design. Despite weighing over 700 tons, these hollow steel engines. The entire lock system was operated from a single, centralized control tower. A massive model console mirrored.
To guide the massive ships safely through the narrow concrete chambers, they designed electric locomotive mules. Running on cog tracks along the lock walls, they would prevent the emissions. The lock chambers required no pumps. By simply opening the valves, gravity forced the water from Gutun Lake to flow down. Gatun Dam successfully blocked the wild Chagres River, creating Gatun Lake, the largest artificial lake of its time. The entire canal was powered by electricity, generated by the water flowing out of Gatun Lake through a specialized hydroelectric grid. By 1914, the master lock system was finished. The concrete had dried, the steel gates were hung, and the water was trapped.
In 1983, the final wall of rock separating Honshu and Hokkaido was blasted away.
The Panama Canal was immediately hailed by the global community. Tributes poured in from National Geographic and architectural semis. The canal reshaped global economics. It slashed the voyage from New York to San Francisco by nearly 8,000 miles. The victory belonged to the 50,000 workers who had endured the heat, the mud, and the disease. Their sacrifice had rewritten the physical map of the world.
The divided continent was now united. The Panama Canal had entered operational history.
But a century later, the battle to maintain and expand this vital corridor continues. In 2016, to address water scarcity, the new locks introduced innovative water-saving basins. 60% of the water used every day, structural maintenance teams use laser scanners to monitor the concrete walls, checking for microscopic cracks under the constant hydrostatic pressure. Furthermore, modern climate change and severe droughts are presenting the canal with a raw test of survival. Low water levels in Gatun Lake limit the draft of transit ships. The Panama Canal is no longer just an engineering channel. It has evolved into a vital climate adaptation center, managing the entire watershed of the nation, standing as definitive proof that when sharp journalistic vision meets peak engineering, humanity can not only challenge nature, it can rewrite the rules of the planet.